Hello everyone and welcome to today's GOAT seminar, where we have the pleasure of listening to the talk of Herman, who will talk about density of group languages.
Thank you. Well, first of all, thank you for the invitation. So the topic I'm going to talk about today, well, what I'm going to present is joint work with these other names that you see there. So Valérie Berthé, Carl-Fredrik Nyberg-Brodda, Dominique, Perrin, and Karl Petersen. And yeah, so let's start with quick introduction. And by the way, don't hesitate to interrupt me at any time for questions or clarifications. My goal is also that you understand something, ultimately, you know. So introduction. So I just wanted to give briefly a bit of history. So this is a topic which was already studied in the past quite a lot, this idea of density of rational languages under some probability measures. And so I give here some name with some years. Maybe I can highlight the name of the Perrin year. Here is the same one that was in the list of authors. So he was the one sort of initiating or reviving the topic, because it's something that he worked on a while ago, and then he wanted to sort of revive it and make new progress. But it was also studied by a bunch of other people that actually he wasn't aware of. And so we sort of discovered that there was this whole literature. Well, some of it was later than him, but some of it, for instance, the work of Veitch was even earlier. So we made some connections with, so there's plenty of literature, I guess, is what I want to highlight here. And it's connected with a variety of topics. So Veitch is like a dynamicist who studies ergodic theory. So it doesn't have things to do with rational languages that much. That's not his point of view. And Lynch is a logician. And so this notion appears in a variety of different contexts, not only rational languages. So my main goals, I want to introduce what are group languages in particular. So they're a special family of rational languages. And I want to introduce the notion of density, tell you what it is. I'm going to talk about ergodicity, which is one of the big conditions that we need in order to prove result about densities. And then if I have enough time, I'll sketch the proof that the densities exist. So once you'll see what densities are, the question of existence will make sense. And then if I have time, which I probably won't, I will hint at the relationship with return words, which is more combinatorics on words topic. Okay, so, and so I put here, don't worry, you don't need to memorize all of this, but just to give you a sort of flavor of all the objects that we'll see during the talk. So I will fix a finite alphabet and a rational language over this alphabet. And I will denote AZ, the set of bi-infinite words, which I view as a topological space with the product topology. And fairly important will also be the shift map, which basically takes a sequence, a bi-infinite sequence or bi-infinite word, and shifts it one rank. And then we will deal with probability measures on AZ, and the notion of density will be denoted like this. But don't worry, like we'll come back through all these notions many times. I'm just sort of preparing you mentally that these will be the main objects. And the support of the measure, we'll need to deal with that too a little bit. So it kind of blends combinatorics on words or rational language and automata theory with something more topological with this space of sequences, and then probability measures come in the mix as well. So let's move on to group languages and densities. So first of all, what is a group language? Well, there's the automata point of view, but there's also very conveniently an algebraic point of view, which is that a group language, I will define it like this, it's a set of the form L equals phi inverse of K, where phi is a morphism from A star to a finite group G, and K is a subset of G. So we fix a group, we fix a morphism from A star to G, which basically just means we're sending each letters to a group element, and we're interpreting words as products in that group, basically. Phi, that's why phi does. It translates a string into a product in our group, and then we take a pre-image of some subset of that finite group. And this is equivalent to being recognized by an automaton where the letters permute the state of the automaton. Okay, this is not completely obvious, but there's this little construction that you can do to pass between this point of view and this point of view. So let's do a concrete example. Here my group is Z over MZ. Well, in that picture, I put M equals 2. And so that's a simple example of group language where my group is just a cyclic group. And I interpret A as +1 and B as +0. And if I take phi inverse of 0, so now I take a subset, one element subset of my group, the language is the set of all words W whose number of A is congruent to 0 mod M. And so for M equals 2, here is how you can view this. So this is my group. The states are the two elements of my groups, and the arrows describe how the alphabet should be interpreted inside of the group. So A swaps the two states, and B fixes them because it's mapped to 0. Okay, so this is additive groups in that case. And well, to get this language, we would need to fix this 0 as both initial and final states. But if we fix different initial and final states, we would get different languages. Okay, so I hope this example is, so this is a very simple language which falls in this category of group languages. But of course, we can do much more complicated things. So here is a morphism from ABC star into the symmetric group on 3 elements, where I map A and C to the cyclic permutation to the 3 cycle, and B to a 2 cycle. So then you can see that you can view this as an automaton where the states are elements of the groups, and each letter acts. So A and C act as 3 cycles, cycles of length 3, and B act as permutation, like transpositions, right? And so for each choice of initial and final states, we would have a different group language determined by this morphism. So there's a lot of group languages, and they can get pretty complicated. So it's a fairly large class of rational languages, okay? And so now I arrive to the second thing. So we're going to look at densities of group languages. So what do I mean by a density? So I'm fixing a probability measure on the space of two-sided infinite words. And I'm defining, this is just a shorthand, mu of a word. So the measure of a word will be the measure of all sequences which begin with that word. So so I have my two-sided infinite word, and I want to look at the portion which is just to the right of 0. And if that portion starts with W, then it belongs in that set, and then mu W is just a measure of that set. And with that convention, we have some nice relations like this. But the relations are not so important. I mean, they're important, but you don't really need to remember them. But just to say that you can also think of probability measures as maps defined on words which satisfy some nice little property. You can sort of abstract this. Now, by definition, the density is this limit. So delta mu of L is defined as the limit on average of the measure of the language intersected with words of length I, and for I equals 0 to n-1, and then you take the limit of this. So it's if you know what that means, it's a Cesaro limit of that sequence. Okay, and so it's a bit of an abstract definition. So to see it in practice, let's start by giving some very basic property to get some sense of what it means. So first of all, delta mu of A star will always be 1, no matter the measure mu, okay? Because basically you will get this will always be equal to 1. Delta mu of L will be 0 when L is a finite language. And this is because we look at longer and longer words. So if at some point there are no words in L, then these will always be worth 0 after a certain point, and this will vanish. So this is okay. It works well with disjoint unions. Proof is not particularly difficult. It's just a property of probability measures. And in simple examples, so here I give a very simple one. So it's not quite the group language in the previous slide. It's even simpler. It's just the W's whose length is congruent to 0 mod m. Well, you can show the density of this language is always 1 over m. So it's sort of, and it's intuitive, right? You would think that the density of words of length, congruent to 0 mod m, you should expect to see them around 1/m of the time under some probability measure. I don't know if that makes sense to you, but so the density sort of captures how abundant something is, but in a sort of asymptotic way. So that's why, of course, A star is everywhere, because you cannot escape it. And this is 1 over m, and finite languages would be 0 because asymptotically it no longer exists. Okay. Let's look at a concrete example. Yes.
I have a nitpick over there. So
yes.
Number 2.
Yes.
I just imagine a language where I take all these one-letter words.
Yes.
Shouldn't it be in the sum?
So yes, what will happen is that. So the thing is, what do I mean? Maybe this is what.
It's the measure will be too small.
Yes.
Oh, I see.
Yes. So the problem is that here you will have, let's say you take all one-letter words. Well, when I is equal to 2, you should do the intersection L intersect A2, which will be empty. So you take mu of the empty set, and this is 0. Okay, so you should do this intersection first. Think about what this intersection means in terms of this set, and then I don't know if that.
No, sorry.
Clarifies. No, but it's good. It's good.
The first element is big, and it's small.
Yes, exactly. Yeah. But this is good question. Okay, great. And so, of course, the problem is we have a limit, and the limit might not converge. And even worse than that, sometimes you have two cases. So this is a concrete example which shows that the existence is not an easy problem, where the limit of these. So I give you 2 languages here. So the first one we already saw. I already told you that density is 1/2. The second one is just a bit more complicated, but maybe it's still intuitive that the density is 1/2. So basically, this language will be a word is in this language if its length is either congruent to 0 or 1, and you will alternate between the 2 depending on which powers of 2 you're between. So if you're between 2 to the 1 and 2 to the 2, this quantity will be 1. So it will be all the words congruent mod 1 in that interval. And then between 2 to the 2 and 2 to the 3, so 4 and 8, this will be 2. So this will be 0 mod 2. And so it will be all even numbered words with even length. And then between 2 to the 3 and 2 to the 4. So on wider and wider interval, it's either odd length or even length. And it's sort of intuitive that we're still keeping something which has densities 1/2 over these intervals. And so the density of L2 is also 1/2. But when you intersect them, you get these very wide interval where the density looks like 1/2, and then these wider interval where they look like 0 because the intersection is empty. And so you have this alternation like this, and you can prove that it breaks the limit, basically. The limit doesn't exist. It will oscillate between 0 and 1/2, essentially. Okay, so I don't know if that was a bit confusing, but this is sort of not too hard to show why the density of the intersection does not exist. Of course, I will point out that this is not a group language. This is not even a rational language, actually. And so we're still not.
Sorry, what does it mean to be a rational language?
Okay. So to be a rational language means to be recognized by an automaton. So an automaton is a structure that looks like this. So you have finite amount of states. You have arrows. Here, of course, it's an automaton where the letters permute the states, but you don't need to have permutations of the state. So maybe I can draw a simple example where you don't have permutations. So you can. So you can.
By an automaton where there is a permutation of the state.
Yeah, so that would be a group language. So here's an example which is not a group language. Let's see, you have B, A. And then to finish having a rational language, you need to fix an initial state. So I can take, let's say, this one. And the final state, let's say I will take this one again. And so the language accepted will be all the words which are a path from an initial state to a final state.
I know automaton.
Okay.
Never seen rational.
Okay. No, but yes. So that's the definition. So it's something accepted by a finite automaton, basically.
So it's a regular language.
It's a regular language.
Oh.
Yes. Those are perfectly synonymous. Yes, I.
Okay.
I see the confusion now. Okay, so you're just not used to the terminology rational. It's exactly the same as regular.
Okay.
So about half of the literature says rational, and I guess it depends which side of the literature you're more used to, but rational, regular, exactly the same. Okay. And so group language is a subclass of this, basically. So it's a subclass of regular languages where you ask that what the letter permute the state. So that wouldn't be it because B is not defined on 2, so this is not a permutation. Okay. Okay. So we were here. Okay, existence is not obvious. And then I wanted to give one more example. So actually, let me move on directly to this slide. So this is an example where I have, I take this word, which when I say ABC to the infinity, I just mean ABC repeated over and over again in both directions. So just the word ABC repeated infinitely. And I define a measure by just saying that, so X has 3 shifts. When you shift it, you get the word BCA. And when you shift it again, you get CA, BCA. And then when you shift it again, you go back to ABC, right? And so I define the measure as this measure. So I just give these 3 points. So this ABC, BCA, CAB, the same weight, 1/3. And all other points in AZ will have weight 0. Okay, so it's kind of a very simple discrete measure. And now I'm taking the set of all words whose number of A and number of B's combined is even. And I want to know what's the density. And so one way to think about the density is in terms of the frequency of visits of each of the states. So I want to know, basically, here's how you can calculate it. You start from 0, and then your words gives you an infinite walk on your group, which you can also think of as an automaton. And you want to record the frequency of visits of whatever element you put in the inverse, starting from 0. So we want to know what's the frequency of 0, of the visits in the state 0. So if I take this one, so when I do this, I do A, B, C. So I stayed twice on 0, but only one time on 1. And it will repeat periodically. So the frequency of visit of 0 is 2/3, right? If you play the same game with this one, well, you do B, C, A, B, C, A, and so on. So this time, it's state 1 that we visited 2/3 of the time. So in other words, the frequency of visit of 0 is now 1/3. And well, if you do the same game here, you will find 2/3. And now what you want to do is you want to average out, take the average of all of this, and that will give you the density. So it will be 1/3 squared, because 1/3 of the time it's 1/3, and 2/3 squared, because 2/3 of the time it's 2/3. And you would get 5/9. Okay, so that always works for discrete measures. Of course, discrete measures are not super interesting, but at least I give you like a sort of intuitive way to think about the density that gives you an effective way of calculating it for the simple case of discrete measures, okay? So you can think of the density as somehow encoding the average frequency of visits when you read words in your automaton. Okay, and so now we're going to try to sort of capture this idea, but in a more general setting where maybe the support of the measure is not necessarily a finite set of points. And so the condition where a sort of similar idea will work is this condition called ergodicity. So I'm going to try to explain a bit what that means. So I'm going to start by just giving the definition. So remember that we had this shift map S, and we're going to fix a probability measure mu on AZ. And we're going to say that mu is invariant, so invariant under the shift, if the measure of the shift inverse of a set B is the same as the measure of B. Okay? So that, yeah, that captures the idea that, you know, shifting something doesn't change. And by the way, the shift is in that case invertible. So we could have taken, it's the same as saying mu of SB equals mu of B. Okay? But it's customary to put the S inverse there.
Why is it invertible?
Because we're working on AZ. The shift is just shifting everything to one rank, and you just have to shift it in the other direction. Yeah. And now the ergodicity condition is asking that if there is a set which is invariant under shift, then this set either has measure 0 or measure 1. Okay? So all the sets which are invariant from the point of view of your measure are either nothing or everything. I mean, not really, but from the point of view of the measure. This is what ergodicity is asking. So this is a pretty classical condition. And I should mention also that not everybody adopts this convention, but for us, ergodic also includes invariance. Whenever I say ergodic, I also implicitly assume invariance. Okay, and some authors do that. I'm not like the only one here. Okay, so those are a bit technical conditions, but, and this is not at all obvious, but I'm going to ask you to believe me here, that ergodicity is actually equivalent to a convergence result. So it's equivalent to all sums like this converging, all limits like this, limits of these average sums converging to this product, which you can think of. So, you know, when you have mu of B intersects C equals mu of B times mu of C, would be saying that B and C are independent. And so here, B and C are not quite independent, but they're sort of asymptotically independent in some sense, because if you average out those B intersect S minus NC, it should be an S minus I. Sorry, it's a mistake in my slide, right? Because it should be the I from the sum. Okay, ignore that. But it sort of captures an idea of asymptotic independence, like a weaker form of independence. And basically measures ergodic if everything has that weak independence property, which is okay. So, and maybe you might sort of see why this condition could help us with densities, because densities also involve these type of sums, right? And so it will turn out that the fact that density exists for group languages can be obtained by passing to these types of sums. And actually, in the 3-point example that we saw, this is basically what we were doing in a sort of very simplified way. Okay, so some well-known examples of measures. So I give you these two conditions, but you might say, okay, well, why do we care? What types of measures, probability measures would satisfy this? Well, the 3-point example is one. It's an ergodic measure. You can check. It's actually pretty easy because it's just a finite measure. So you can sort of check just by hand that it works. And it satisfies really those two conditions. Bernoulli measures satisfy those conditions as well. And actually, Markov measures or Markov chains, which you can think of as measure on infinite words. And when you do that, you find out that irreducible Markov measures satisfy the ergodicity condition. Okay, so there's plenty of examples of measures which satisfy these nice properties. Now I'm going to give you another example of such a measure, which is what I call the Fibonacci ergodic measure. And so this is really a more difficult measure to construct because the rule is sort of hard to really describe with finite data. But basically what you do is, so you should read this graph as when you go, when you read a path like this and you stop at a node, this will be the measure of this will be mu of W basically. So here I'm telling you that mu of BA is lambda to the -2, where lambda is a golden ratio. Okay, and you can check that this, and when the path is not in the tree, so for instance, BB is not there, it means that the measure is 0. Okay. And so, of course, I didn't tell you how I built this tree, but there is actually a rule for building this tree and for continuing this tree. And you can check that when you build it like this, the measure is indeed an ergodic. This is indeed a probability measure. First of all, it's not obvious. So, but you can check it. And it's an ergodic measure. And the support of that measure is actually generated by a rule like this. So the rule is, it's a substitution rule, which produces an infinite word. And using that infinite word, you can generate the support of that measure. So the support of this measure sort of naturally arises from this combinatorial construction. Okay, I'm not going to give more details, but this is just to say that ergodic measures arise very naturally also when you start studying these infinite words produced by substitution rules. Okay. There's another, I put a second example, which is another very famous example, which is the two-immorse measure, which is supported on this time an infinite word produced by that substitution. And okay, the measure looks a bit different. And again, it's not exactly, I didn't tell you how, but you can continue this tree and this defines another ergodic measure. So there are plenty of examples, and those examples can have very subtle and complicated combinatorial structures. And this is actually a very general theorem, which says that for every primitive substitution, I shouldn't have used phi maybe, because anyway. So for every primitive substitution, there exists a unique ergodic measure supported by something generated by that substitution. So in addition to Bernoulli and Markov measures, there is this whole family of ergodic measures, which is generated in a combinatorial way, which is a topic very studied a lot in combinatorics on words. And so I give you two examples, Fibonacci and two-immorse, but actually the 3 points example with ABC to the infinity is generated by this substitution. And so, yeah, so this covers quite a large class of ergodic measures. And so with this, we can also, so with these measure diagrams, like I showed you for Fibonacci, you can have a sort of visual depiction of what computing these densities for these more sophisticated measures could look like. And so basically the calculation now, so remember it's these, so delta mu of L is this average sum of mu to the L intersect AI. So L intersect AI, the measure would be just the sum of these columns. Okay, and so what we need to do is we need to take the sum of these columns, not of these columns, but of the elements of these columns, which correspond to words in my language. Then I sum these columns, and then I take an average, and I take the limit of these averages. So this is not at all easy to calculate. And so here I took again the example of set of W where the number of A's is even. And so I circled or rectangled, I guess, something, the elements which belong to that language. Okay, so for instance, here, of course, the empty word belongs to that language, and then B still belongs because B has an even number of A, but BA doesn't. And BAB doesn't, but BABA does. Okay? And so this is not at all obvious how you, first of all, it's not at all obvious how to predict if there will be a lot of or very few of them in each column, and actually it will vary pretty wildly. And here you have sums of inverse powers of golden ratios. It's very messy to calculate, but by some incredible miracle, actually the density exists and converge to 1/2. So this was a very nice example, and we know how to prove it, but the proof is not at all obvious. And it really relies on the fact that mu is an ergodic measure.
So it does not rely on the golden ratio, so it's not just for Fibonacci, but you can prove it for
exactly
all 1 over Z, I guess?
Yes. Okay. Yes. At least substitutive ones.
Mm-hmm.
Outside of the substitutive case, it's get more complicated, but yes, so okay. And so actually this was another comment that, and actually we can prove a bit more. So some measures like the Fibonacci measure would be one of these examples. It's a measure which has this property which we call equidistribution, which is that the densities of various group languages defined on the same group are uniform. Okay, so if we come back to this, so since this one congruent to 0 is 1/2, then congruent to 1 also needs to be 1/2. But actually this rule will work for Fibonacci for any group that you can choose. And so Fibonacci, despite the measure being quite complicated and with messy numbers, turns out that when it comes to density of group languages, we find this sort of very surprising thing where the densities will be equally spread inside the group, which sort of means, in a way, that when you read a word from the support of that Fibonacci measure, then you can expect it to behave like a random sequence from the point of view of the group, because it is as likely to visit any state of your group as any other, on average. So this is quite a strong property and maybe a bit surprising, I would say. Okay, so I hope this was not too much, but we still have a bit more to do. So now I wanted to give some flavor of how can we prove the existence. So how can we prove this theorem? So for every ergodic measure mu and for every group language L, delta mu of L exists. And moreover, the proof leads to explicit formulas in certain cases. And more importantly, it can be used to prove this equidistribution property for the Fibonacci measure, okay, and other measures as well in the same. So there's basically a large class. So Francesco mentioned, did you say epistromian? Arnaud Rosy? Yeah. Well, so there's a very wide class of measures which will satisfy this equidistribution property, and it all follows from actually the proof of this existence theorem. Okay, so the key part of the proof is actually to consider a specific object called a skew product. And so we're fixing, so when we look at a group language, remember it's the same as fixing a morphism from A star to a finite group, and then taking the preimage of some subset. So we're going to fix the morphism, and we're fixing our measure mu. Maybe here I should say ergodic, but for this definition, we don't need ergodic, of course, just a definition. And we let X be the support of mu. And so we're going to define a new transformation. So a transformation on G times X. And the transformation is defined on the X component. It acts like the shift. But on the G component, it acts by multiplying by the image of x0, little x, where little x is my element. Okay, and so if I apply it twice, then here I would get x shifted twice, and here I would get g multiplied by phi of x0 multiplied by phi of x1, because it would be phi of the 0 index element in the shifted sequence, which is 1. Okay, and so basically this structure, really what it does, it captures this idea of walking in the group along my sequence. Okay, so I have along my infinite words. So this will record the infinite word. This records the infinite word along which I'm walking, and this will record the actual walk in the group. And this is a structure that's fairly standard in the theory of dynamical systems in general. It's a very general type of structure, which are called skew products. And we need a small definition. So we'll say that a measure mu bar on this skew product lifts the measure mu if it satisfies this condition. Okay, so mu of G times B is mu of B. So it basically, so if you did a bit of measure theory, whenever you have a map between from a measurable space to somewhere, you can sort of take an induced measure. You can project the measure along a map. And so here you would say that mu bar projects to mu along the natural projection from G times X to X, the component. But okay, this is a definition. And it's not hard to see that you can build at least one measure which projects to mu, which lifts mu, which is the product measure, nu times mu, where nu is the uniform probability measure on the group G. So G is a finite group. We can take the uniform probability measure and we can take the product measure. So let's do an example. Here we have, so I'm going to give you an example of what this transformation looks like in the 3 points example again. So I give my morphism here. It sends A and B to 1 and C to 0. Here is what X looks like in sort of diagrammatic form, right? Here you should imagine that you should add like an infinity. This is just a shorthand. And so here's how the shift map acts on my 3 elements. And here are the measures of each element, right? And to the right, you have the skew product. So elements of the skew product are pairs, one element of the group times one element of the shift, one element of the support of the measure. And when you apply the transformation, what you do is you shift this sequence and you act on this component by the first letter. So since A is mapped to 1, you should do +1 when you start from here. So you end up in this component. Since B is also mapped to 1, you go to this. But since C is mapped to 0, it doesn't switch sides. So that's why 0 CAB goes here. And the same thing happens for the other 3 elements. And then the measure, the product measure, is just the product of 2 uniform measures in that case. So the measure is 1/6 on each point. So you can see that in that case, the construction of the skew product is fairly simple. It just duplicates the shift, basically. It duplicates the support of. So I keep saying shift because the supports of these probability measures are often called shift spaces, or shifts for short. So that would be a terminology for X, but I didn't introduce it. So, okay. But in practice, skew products can get way more complicated than this. And in particular, they can get very complicated when the support of the measure is infinite. They're hard to depict or understand. Okay? And so now, what is the basic idea behind the proof of existence? I'm not going to give you details, but basically, so we have the density, which I put again the formula here, which looks like this. And here I put what it would mean for a lifted measure mu bar to be ergodic. So ergodic would mean that these sums converge to some product, right? Yes, I just copied the same formula, so yes.
Well, it's not the same as S there. Now it's T.
Yes, it's not the same, you're right. So what happens is that I copied the formulas and I changed mu to mu bar and S to T. Okay, but the definition of ergodicity, but I didn't change N to I because really I didn't realize that there was a mistake there. And okay, well, but you're right that it's not quite the definition of ergodicity that I gave, but it's not hard to see that actually this notion of ergodicity, you can apply the same definition whenever you have a space with a transformation, right? We didn't use anything specific about S. And so I'm going to say that, mu bar would be an ergodic measure when all of these sums would converge.
So for the transformation, it has to be a measurable function or something like that, at least?
Yes, in that case, since we deal only with Borel measures, we can even say continuous. In our case, it's even simpler because everything is continuous. And so I didn't mention it, but yes. But yeah, in general, you would need it to be measurable. And so now the proof is basically just two steps. The first part is to prove that there is a lift mu bar, which is ergodic. And the second part is to prove that the density can be broken down as a sum of these ergodic sums. And then by ergodicity, the ergodic sums converge, and we're done. Now, of course, both of those steps require work, right? And I'm not going to go into it because it's a bit technical, but really the big idea is quite simple, is that you sort of lift your problem in the skew product, and then you transform your problem into convergence of ergodic sums. And this, we know that it's a very well-studied condition, ergodicity. There's books about ergodic theory. And so now that we lift the problem to the skew product, we now have unlocked all this machinery of ergodic things, and then we get basically for free. And I should say that, the definition, so there's clearly a gap between the definition of ergodicity that I gave and the fact that it means that all of these ergodic sums converge, and this gap is highly non-trivial. Okay, to pass from the more basic definition to this convergence thing is a very difficult. It comes from a theorem which is called Birkhoff's ergodicity theorem, and so really this proof uses a lot of machinery from this ergodic theory, but applied to this very sort of, you could say, like discrete automata theory kind of problem. So we were pretty happy to have this argument there to give. So this covers, this proof existence for the Fibonacci measure, for the Twimors measure, for all Bernoulli measures, for all group languages. So this is quite a very general argument. And the nice part is that, so here we say, well, we have at least an ergodic lift, but if it happens that this product measure mu times mu is the ergodic lift, actually when you do this passage from density to ergodic sums, and when you do the calculation for this specific measure, everything simplifies down to a very simple formula, which is the equidistribution formula I mentioned. And so when it happens that when you lift to the skew product, this becomes ergodic, then you get this equidistribution result. And so it holds for Fibonacci and for a very wide class called dendritic substitutive, which I won't go into. But in general, it fails if G times X has non-trivial subsystems. And so we've seen an example. So that's why So remember, we calculated that the density was, well, maybe you don't, but the density was 5,9. So it means that the result was not equidistributed. And this is precisely because this system, the skew product, splits into several subsystems. And then we can go deeper into this, like try to figure out, okay, if it splits, can we still get formulas for the density? And the answer is yes, but it's 45 minutes. So I'm gonna skip the rest and stop there with a very quick slide where I give some things that are related with what I talked about that I didn't have time to touch on, and also some future projects, including, of course, so we did it for group languages, and the question is, can we prove, for instance, existence and get equidistribution results for general rational languages? So this is something that we're working on. And I'm going to stop here. Thank you.
Thank you very much. Are there any questions? Tomasz?
No pressure, but
Or anybody else?
Actually had this question before, but now it's written there at the second item. I'm quite curious. What about biphase decoding?
So, yes, this is not completely clear because the problem yes, when you do bifix decoding, the problem is that you pass from, let's say you start with your group language, but using bifix decoding, you're no longer with the group language. You are with the rational language, and now things get more messy. But there is definitely a link, which we can sort of apply in the group. I don't know, I think my answer is not very precise, but basically there is a link, but the link requires to pass to general rational languages at some point.
But you know that there are some families like the dendric or other families that actually are preserved by biphase decoding. So
yes, but I mean, so what I think. So the thing is, maybe we're not talking about exactly the same bifix decoding, because what I meant is when you have a group language, then you have a group code, and then you have therefore a bifix code. And then when you intersect this bifix code with your language, you get a new bifix code, therefore a new rational language, with the language of the support of the measure, I mean. So I think I'm not being...
Okay, no, but I guess it's probably a...
Yes, we can maybe we'll talk about it in more details when, yeah.
So I noticed that you did some work on Schützenberger business.
Yes.
So is there a relationship of this and the Schützenberger product?
So the Schützenberger business is, I think, maybe not related. I think the problem is that the word Schützenberger has many meanings.
Yeah.
And I don't think it's exactly...
One of the labels that I recognize.
But no, I don't.
No.
I don't think so. Well, maybe, but since I'm not sure. So Schützenberger product is an operation on automata, right? Mm-hmm. Sort of unambiguous product, am I correct? So I'm not sure. It's a good question.
I mean, I just noticed that you were doing
yes.
two types of products. So, well, not really. One was the Schützenberger business.
Yeah.
Are there any other questions? Tomasz? Okay, so if not, let's thank the speaker again.